And this next section is about symbolic arguments. So the idea is you can think of most of your papers you've had to write, whether it be for history, whether it's for English, something along those forms. You've had to come up with some type of argument, combine those to make a conclusion. Same thing happens here. So a symbolic argument consists of a set of premises and a conclusion. Okay. So an argument is valid when its conclusion necessarily follows. From a set of given premises. Okay. An argument is invalid or called a fallacy when the conclusion does not necessarily follow. So I'm going to cheat. So when its conclusion does not necessarily follow. From a given set of premises. Okay. So basically, the conclusion has to happen for you to be valid. You always have to be right. No matter whether statement P or Q is true, you have to be right at the end. So let's kind of work with a real life example so you can kind of see what we mean by this. So let's consider two statements. So our first premise, premise one, is if we go to the movies, I'll buy popcorn. Okay, so this is a statement that could be true, could be false. Okay, the second premise is we go to the movies. So if you just think, if I make the statement, if we go to the movies, I'll buy popcorn, then I make the statement, we go to the movies, the conclusion that's going to make sense is we're going to the movies, so I'm going to buy popcorn. Okay, so this makes sense naturally. So what we're going to try to do is put this in symbolic form. So I'm going to call we go to the movies statement P. And then statement Q is I buy popcorn. Okay. So in symbolic form, the argument is we've still got conclusion one, or premise one and premise two, and our conclusion. So in this symbolic form, we have a conditional statement to start. So if P happens, then Q happens. The second premise is P. The conclusion we make is Q. Okay? So what you're typically going to see is just this symbolic form, and the conclusion is going to be underneath a bar. And you put these three little dots to say, therefore. So the way you kind of want to dissect it is this stuff happens. Therefore, this happens. Okay. So the other way you can think of it is if these premises hold, then this conclusion has to hold. Okay. So we really end up creating a single statement based off of this argument. So basically, if premise 1 and premise 2 happen, then this conclusion happens. So we can also write this argument as follows. If premise 1, which is our conditional, and premise 2 happen, then our conclusion has to happen. Okay. So you can think of that if premise 1 and premise 2 happen, then the conclusion happens. Okay. And so every single symbolic argument you can turn into a single logic argument using this idea. The premises happen, then the conclusion. Okay. So ultimately, this makes sense verbally in terms of this popcorn argument. What I can do is I want this argument to always be true. So I'm going to look at a truth table for this. And if that truth table always results in true, then I'm good and my argument is going to be valid. Okay. So ultimately, we can construct a truth table to see if the statement is always true. Okay. So I've got my two statements, P and Q. I've got my first premise, which is if P, then Q. And then I want to see premise 1 and premise 2 together. So before I can apply this main operation here, I need to figure out what the truth value of my premises is together. So I'm going to do what's in the beginning. Once I then have my truth value of my premises combined, we can go ahead and do this full statement at the end. Okay. So unfortunately, these do create some gigantic truth tables. But it's two statements. So luckily, just going to be the 4 columns. And it looks worse than it is. There's really not too many rows we have to fill out. Okay. But our beginning statements of we go to the movies and buy popcorn can be all of our same combinations that we're used to. Okay. So I'm going to start by finding premise 1. We want if P, then Q. So again, we're starting with P, going to Q. So this is giving me, based off these combinations, the truth value of if we go to the movies, then I'll buy popcorn. So going through that, again, my only problematic case is here. Everything else is true. Okay. Now I want to find my truth value for premise 1 and premise 2. So I put my truth values for premise 1 first. We're doing premise 1 and premise 2, which is true, false, for Q. So here they're both true, so my end statement is true. Oh, and I put the, yeah, no, I'm good, okay. Oh, that's why I put the wrong thing here. I'm like, that doesn't make sense. I want to put P. Premise 2 is we go to the movies, not I buy popcorn. So I got to put my right truth values of P, which are true, true, false, false. Okay. So premise 1 and premise 2 is true in the first position, but in all of these other places, it's false. Okay. So going through now my final argument at the end, I want to put my truth values for my two premises. So here, this is going through if premise 1 and premise 2, then the conclusion happens. Okay. So I'm going to put all of these truth values at the beginning here. So it's true, false, false, false. Then we're putting the truth values for a conclusion, which is true, false, true, true. So these values represent the truth value of the stuff at the beginning. So now I can find my end statement. If I start out true, I better lead to true, and I do. I don't have any of the problematic cases where I start true and lead to something that's false. So all of these are true. Okay. So no matter if I do go to the movies or I don't, or if I do or don't buy popcorn, I'm always making a valid argument by making this statement. So if we go to the movies, then I buy popcorn, and we go to the movies, then it has to happen that I buy popcorn. Okay. So this end statement is a tautology. Okay. So what that means is this argument is going to be valid. Because I always make a true statement in the end. Okay. So we're going to go through a few more examples today, but that's pretty much all this section is about. So we started talking about arguments and whether an argument is valid or not. So basically you make some statements that happen or not, and then a conclusion is going to naturally have to follow. So we have a way to turn this argument into a single logic statement that we want to see, is it always true? So I'm going to do probably like 3-4 more examples of this. We'll do one with words as well that we're going to turn into symbolic form. We're going to determine if the argument is valid. Okay. And the first one we're going to do is we have the premises P or Q. Then we've got not Q. And the conclusion that's going to follow, remember this means therefore, P has to happen. So basically, if this and this happen, then P has to happen. So we can turn this into symbolic form. As follows. Okay. Basically have a giant if-then statement. We've got premise 1, which is P or Q, and premise 2. If these happen, then the conclusion has to happen. So I'm going to write it in words as well. But if premise 1 and premise 2, then the conclusion has to happen. Okay. So pretty much every single argument, you're going to have a giant if-then. You've got premise 1, premise 2, and abbreviate. They both have to happen. Then your conclusion happens. So this is our setup every single time. Okay. So I just have two statements, or two statements, P and Q. We've got to find the truth value of premise 1, so that's P or Q. We got to find the truth value of premise 2. Then we want to find their combined truth value. And then we can go to this giant statement, which is our actual argument. Because we have that end conclusion already written down as well. That is just P. And so we have 4 possibilities. So 4 rows in our truth table. 90% of the problem is just setting up this truth table. And take your time with these, because you make one small tiny true when you should have put false, and it doesn't go as well. So we run through our standard both true, true, false, false, true, false, false. Now I want to look at my statement P or Q. So we'll put statement P here. Put statement Q here. And we're doing or. So is P or Q true? You need at least one to be true. And so just as in case you get something that's false. For not Q, we just switch these truth values. So false, true, false, true. So now I've got premise 1 here, premise 2 here. I want to see, are both premise 1 and premise 2 true? So we'll put our values of premise 1 first, true, 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 false. We want premise 1 and premise 2. Okay. And so going through this, for n to be true, they both need to be true. That only happens here. So that's the only true. These are all false. Okay. And now we are good. We got everything we need. We have the truth values of this. We have the truth values of this in each row. We can go ahead and do this if-then statement. So we're going to put the truth value of our premises combined, and we're doing an if-then statement. And then I want to put the truth values of P here. Okay. So the only bad case is when you start true and go to false. That doesn't happen. So all of these are true. Okay. So remember, true to false is the bad case. That's where you get an A, but I did not buy you a car. Okay. So in the end, no matter the starting values of P and Q, the statement I make for this argument is always true. So this argument is valid. Okay. All right, let's try some more. Second argument, we're going to change the words up a little bit. We're going to do if A, then B. Not A, that's not an A. Therefore, the conclusion that has to happen is not B. So again, I want to put this in symbolic form first. We've got premise 1 and premise 2. Then our conclusion has to happen. So I've got two statements, A and B. I want to find premise 1. I want to find premise 2. I want to find them together. I need my conclusion before I can do this full statement. So I need to put not B here. And then I can go ahead and do this full argument. Give myself a little room. Okay. So quite a large truth table this time, but that's okay. I still only have two statements though. So I have 4 rows in my truth table. So I start with my same values, true, 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 false, false, true, false, false. I want to do A to B. So I'm not gonna write them all here, but basically I'm putting an arrow in between each of these. This is my bad case. Everything else is going to be good. For not A, I go ahead and change all of my values for A. So false, false, true, true. Now we want these two combined. So I'm going to put the values of our first premise. We want premise 1 and premise 2. And so these would both be false, but these next two, they're both true. So the end is true. Now I have to change the truth values for B. So this is going to be false, true, false, true. And now I'm going to put an arrow in this direction. And you see we have our problematic case. But I'll go ahead and put each of those in here. False, false, true, true for the premises. We're making this conditional statement for our argument. And then putting the values of not B. So this is our problematic case, but the other values are true. But regardless, if I start with this combination, my argument is going to be false, and I don't want that. So since the argument is not always true, this is invalid. Okay. All right. Now we've got a doozy of one because we're going to do an argument with 3 statements in it. So for C, our first premise is a biconditional, which is P if and only if Q. Then we've got Q and R. And the conclusion that's going to happen then is P or R. So in symbolic form, this is going to be premise 1 and premise 2, then the conclusion. Okay. So quite a large truth table because we've got to go through statements P, Q, and R first. Okay. Then I can go through my first premise, which is P if and only if Q. Look at the truth value of our second premise. Then we want to look at their truth values together. Okay. Then before I can do this full thing, I need my conclusion. And then we go ahead and just put an arrow in this direction. I need to shrink this down to be able to fit everything. Then we've got our full argument in symbolic form. So I'm going to go ahead, there we go. So quite a large statement. You might need to do this like sideways on a paper to fit it in. Now the other fun thing is there are 3 statements. That means I have 8 possibilities. So I need to make 8 rows in my truth table. So that's 4, 5, 6, 7, 8. So quite a large truth table for this argument. Let me go ahead and got to make all of these columns as well. So I will be super careful with this one. So we definitely do not want to make a mistake midway through and then everything be off. So remember, we start with 2 of the statements and run through our full possibilities. Then P could be true for all of them. And then we run through the same 2 possibilities again. And now P is false for all of them. Okay. So our first one, we're doing P if and only if Q. So we're putting a double-sided arrow between each of those. Again, I'm going to start by putting all of P's values first. We're doing the biconditional, so double-sided arrow, which means they have to match. And then we put Q, which is true, true, false, false, true, true, false, false. So for the double-sided arrow, you need both of them to be the same. So these are true, but these aren't the same, not the same, not the same, not the same, then both the same. So it's true when they're exactly the same thing. Now we move into Q or R's, or Q and R. So we're putting an and symbol in between each of these. So I'll start by putting Q's truth values, true, true, false, false, true, true, false, false. And then an and symbol and R, which just alternates true, false, true, false, true, false, true, false. Okay. And means they both have to be true, which only happens here. And none of the others are they both true. So the rest are false. Okay. Now we want to see, is premise 1 and premise 2 true? So we're utilizing both of these to get this next column. So I'm going to put my values of premise 1. We're doing and. And then premise 2, which is true, false, 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 true, false, false, false. And so only here are they both true. Everywhere else, it is false. Okay. Now I've got one more that we still have to do before we can go through this full thing. I need to find the truth value of my conclusion. So I want to put my values of P, which is true, 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 false, 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 false. And we're doing or. And then we put our values of R, which is true, false, true, false, true, false, true, false. For or, you just need one to be true. Here, you've got none that are true. This one's good. This one has none that are true. And now after all that work, we could finally talk about our argument. So we're putting an arrow in this direction. So we've got true, and the beautiful thing is you're pretty much starting false for all of these end ones. And if you start a conditional statement with false, so you did not get an A, what I do really doesn't matter for any of those cases. This is the only one that's important because you did get an A, but I did buy you a car. So we can put all of the values here. But again, this is the only one we really need to check because that's one that starts out true. The others make no difference because you did not get an A. So whatever I do doesn't matter. I didn't break my promise, and I end up with something that is always true. So again, this argument is valid. Okay. So I have one more. And we're going to get some more practice with translating it into a statement first. And then we'll go ahead and see if I've made something that's valid. And then our next section is going to be kind of nice. It's a very different type of argument, but I think it's a little bit easier to comprehend. So we're going to translate the statement into symbolic language and determine if the argument is valid. Okay. So what we're going to be doing is that our argument is going to be kind of strange. A tiger is a cat, and a giraffe is not a dog. A tiger is not a cat. Or a giraffe is not a dog. Therefore, a tiger is not a cat. So if I just spewed this out to you, you probably would think I would be crazy. But we've got two kind of main statements that are popping over and over along with their negations. One being a tiger is a cat. The other being a giraffe is a dog. Okay. That word not you want to indicate means the negation of something. So if we go ahead and look at this argument, in this logic form, our first statement is a tiger is a cat and a giraffe is not a dog. So a tiger is a cat is our statement P, and a giraffe is not a dog. So that is not Q. Second statement is a tiger is not a cat or a giraffe is not a dog. So that's the opposite of statement P. We've got the or and the opposite of statement Q. Therefore tells us we're now talking about the conclusion. And the conclusion we make is a tiger is not a cat. So that is the opposite of statement P. So in symbolic form, as a single logic statement, this argument can be condensed as our first premise and our second premise. Then this conclusion has to follow. So I want to go ahead and see, is this end statement going to be true, no matter what the truth values of the first ones are? Okay. I need to leave that up there a little bit. We've got two statements, P and Q. Before I can find our first premise, I need to find not Q. Then I'll go ahead and find premise 1. Then we got to figure out what not P is before we can find premise 2. So really, if you want, we can reorder this a little bit. You've got the two statements, go ahead and just put their negations next. Now I can find premise 1. We can find premise 2. We can find premise 1 and premise 2 together. And now we have everything we need to be able to talk about the full argument. Okay. All right. And luckily, this is only two statements, not 3. So I only have 4 columns in my truth table, which is way better. Give myself a little more space. But we have a lot of work to do. Okay. So I'm going to start with all of my truth values first. We've got our standard true, 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 false, false, true, false, false. And then immediately I can just negate these. So false, false, true, true, false, true, false, true. Okay. Now I'm going to start with my first premise, premise 1. So I'm going to put my values of P, true, true, false, false, and then my values of not Q. So false, true, false, true. And we're doing the AND operation. So this is the only spot where they're both true. The remainders are false. Then we move on to premise 2. So I've got to put not P first. Then I've got to put not Q. which is false, true, false, true. And here we're doing the or. Okay. So as long as one is true, they're both, the or statement is true, which happens in these ones. Okay. Now we go ahead and do premise 1 and premise 2. So we'll put premise 1's values first. Then we'll put premise 2 values. And we want the AND operation, premise 1 and premise 2. This is the only spot where they're both true. So the remainders are false. Okay. Now I'm good to go ahead and talk about my end conclusion. So I want to put my premises first. I want to put my conclusion, which is not P, which is false, false, true, true. And we're doing our conditional. And so we've got a problem. We've got that case where you got an A, but I did not buy you a car. This part is false. The others are true though. But ultimately that doesn't matter because I end up with a false. This argument is invalid. Okay. So this statement doesn't actually work. It's not always the case.